Understanding UPS efficiency calculations is crucial for assessing the performance and cost-effectiveness of your uninterruptible power supply systems. The basic principle behind calculating efficiency is to compare the power output to the power input, expressing the result as a percentage. This allows you to determine how much of the input power is actually used to power the load, versus how much is lost in the conversion process, typically as heat. The fundamental formula for efficiency is efficiency equals power output divided by power input multiplied by 100%. This gives you the efficiency as a percentage. However, calculating the input and output power for a three-phase UPS system requires a deeper understanding of three-phase power concepts. Firstly, let's discuss three-phase power calculations. Three-phase power is used in many industrial and commercial applications due to its efficiency in delivering power. Unlike single-phase power, which has a voltage that varies like a sine wave, three-phase power consists of three alternating current voltages that are offset by 120 degrees. This provides a more constant and efficient power supply. To calculate the total power in a balanced three-phase system, you can use the formula power equals the square root of 3 multiplied by the line-to-line voltage, multiplied by the line current, multiplied by the power factor. The square root of 3 is approximately 1.732. The line-to-line voltage is the voltage measured between any two phases. The line current is the current flowing through any one of the lines. The power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amperes. It represents the efficiency with which electrical power is used. A power factor of 1 indicates perfect efficiency, while a lower power factor indicates that a portion of the power is being used to create reactive power, which does not perform useful work. Now let's address the difference between phase current and line current. In a three-phase system, the terms phase and line refer to different aspects of the current flow. Phase current refers to the current flowing through a single winding of the generator or transformer. Line current refers to the current flowing through the conductors that connect the source to the load. In a Y-connected system, the line current is equal to the phase current. However, in a delta-connected system, the line current is equal to the phase current multiplied by the square root of 3. This difference is important to consider when calculating power, as you need to use the appropriate current value in your calculations. Now, let's consider the specific data provided for the UPS systems. The data includes input voltage and current for phases A, B, and C, as well as output voltage and current for the same phases. It also provides the displayed kilowatt and kilovolt ampere values. To calculate the input power, you'll need to use the three-phase power formula mentioned earlier. However, since you have individual voltage and current readings for each phase, it's more accurate to calculate the power for each phase separately and then add them together. The formula for power in each phase is phase power equals phase voltage multiplied by phase current multiplied by the power factor. To find the total input power, sum the power of each phase. Total input power equals phase A power plus phase B power plus phase C power. Since the power factor is not explicitly provided in the data, you'll need to either measure it directly or estimate it based on the type of load connected to the UPS. In many UPS systems, the power factor is assumed to be around 0.8 for typical loads. If the kilovolt ampere value is provided, you can calculate the power factor by dividing the kilowatt value by the kilovolt ampere value. The formula is power factor equals kilowatt divided by kilovolt ampere. Once you have calculated the input power, you can calculate the output power using the same method. Use the output voltage and current values for each phase to calculate the power for each phase, and then sum them to find the total output power. Now, let's address the issue of negative losses observed in Unit B3. This is likely due to inaccuracies in the measurements or inconsistencies in the data. It's also possible that the UPS is operating under conditions that are not accurately reflected in the data, such as changes in load or input voltage. Firstly, double-check the data to ensure that the voltage and current readings are accurate and consistent. Secondly, make sure that the measurements were taken under stable operating conditions. If the load or input voltage was fluctuating during the measurements, this could lead to inaccurate results. Thirdly, consider the possibility that the UPS is using a different formula to calculate power than the one you are using. Some UPS systems use more sophisticated algorithms to account for nonlinear loads or other factors that can affect power measurements. Refer to the UPS manual or contact the manufacturer for more information on how the UPS calculates power. Here's a step-by-step approach to calculating UPS efficiency. Firstly, gather the necessary data, including input voltage, input current, output current, kilowatt, and kilovolt ampere values for each phase. Secondly, calculate the power factor using the formula power factor equals kilowatt divided by kilovolt ampere, if the kilovolt ampere value is available. If not, estimate the power factor based on the type of load. Thirdly, calculate the input power for each phase using the formula phase power equals phase voltage multiplied by phase current multiplied by the power factor. Fourthly, calculate the total input power by summing the power of each phase. Fifthly, calculate the output power for each phase using the same formula, but with the output voltage and current values. Sixthly, calculate the total output power by summing the power of each phase. Seventhly, calculate the efficiency using the formula efficiency equals power output divided by power input multiplied by 100%. Finally, analyze the results and identify any potential issues, such as negative losses or unusually low efficiency values. If you encounter any problems, double-check the data and calculations, and consult the UPS manual or manufacturer for assistance. Let's illustrate with an example using the provided data for Module A on. Input voltage phase is 466 volts, input voltage phase B is 469 volts, input voltage phase C is 466 volts. Input current phase is 259 amps, input current phase B is 276 amps, input current phase C is 260 amps. Output voltage phase is 483 volts, output voltage phase B is 480 volts, output voltage phase C is 482 volts. Output current phase is 168 amps, output current phase B is 219 amps, output current phase C is 183 amps. Displayed kilowatt is 153 kilowatts. Displayed kilovolt ampere is 157 kilovolt amperes. Firstly, calculate the power factor. Power factor equals kilowatt divided by kilovolt ampere, which equals 153 kilowatts divided by 157 kilovolt amperes, which equals 0.97. Secondly, calculate the input power for each phase. Phase power equals 466 volts multiplied by 259 amps multiplied by 0.97, which equals 184.78 watts or 117.18 kilowatts. Phase B power equals 469 volts multiplied by 276 amps multiplied by 0.97, which equals 125,582.52 watts or 125.58 kilowatts. Phase C power equals 466 volts multiplied by 260 amps multiplied by 0.97, which equals 117,432.2 watts or 117.43 kilowatts. Thirdly, calculate the total input power. Total input power equals 117.18 kilowatts plus 125.58 kilowatts plus 117.43 kilowatts, which equals 360.19 kilowatts. Fourthly, calculate the output power for each phase. Phase power equals 483 volts multiplied by 168 amps multiplied by 0.97, which equals 78,846.12 watts or 78.85 kilowatts. Phase B power equals 480 volts multiplied by 219 amps multiplied by 0.97, which equals 101,788.8 watts or 101.79 kilowatts. VC power equals 482 volts multiplied by 183 amps multiplied by 0.97, which equals 85,476.42 watts or 85.48 kilowatts. Fifthly, calculate the total output power. Total output power equals 78.85 kilowatts plus 101.79 kilowatts plus 85.48 kilowatts, which equals 266.12 kilowatts. Sixthly, calculate the efficiency. Efficiency equals 266.12 kilowatts divided by 360.19 kilowatts multiplied by 100%, which equals 73.9%. This calculation provides an estimate of the UPS efficiency based on the provided data. Remember to verify the accuracy of the data and consider any potential factors that could affect the results. One more thing to consider when evaluating UPS efficiency is the load level. UPS systems typically have a higher efficiency when operating at or near their full load capacity. When the load is significantly lower than the rated capacity, the efficiency can decrease due to the fixed losses associated with the UPS components. To accurately assess the efficiency of your UPS systems, it's important to measure the power input and output under different load conditions. This will give you a more complete picture of how the UPS performs in various scenarios. In addition to the load level, the age and condition of the UPS can also affect its efficiency. Over time, components can degrade, leading to increased losses and reduced efficiency. Regular maintenance and timely replacement of worn components can help maintain optimal efficiency. Also consider the type of UPS technology being used. Different UPS topologies, such as online double conversion, line interactive, and offline standby, have different efficiency characteristics. Online double conversion UPS systems typically have lower efficiency compared to line interactive or offline standby systems due to the continuous conversion of power. However, they offer better protection against power disturbances. Line interactive and offline standby UPS systems have higher efficiency because they only switch to battery power when a power outage occurs. When selecting a UPS, it's important to consider the trade-offs between efficiency, protection, and cost. Choose a UPS that meets your specific needs and provides the best balance of these factors. By understanding the formulas and factors that affect UPS efficiency, you can make informed decisions about the selection, operation, and maintenance of your UPS systems. This will help you reduce energy consumption, lower operating costs, and improve the reliability of your power infrastructure.